Just forget that. All right, we'll give people another minute or so. Let's see who I've got. Got a few people here. All right, so why don't we start? One thing I should have said last time, but didn't, though I used it, so I want to go back and just fill in the gap. Suppose we have an element in GL in the integral group ring of G, and suppose its class is 0 in the Whitehead group of G. Then after stabilizing M, so let's replace M by something I'll call M tilde, which is M plus an identity matrix of some large but finite size. So this is then an element, just the image of the element M in a larger matrix group, right? So it's M here, 0, 0, identity. So just the inclusion of M into some larger group. Then this image can be transformed by elementary column operations to the identity matrix of this size, where the elementary column operations are multiply a column or the first column, doesn't matter, by plus or minus a group element, or add an arbitrary ZG multiple of, let's say, column 2, well, not column 2, of a column to another. So you have one column, you have two columns, you're going to take a multiple of the second one and add it to the first and leave all the other columns alone. These are your elementary column operations. These include, for example, permuting the columns. So I can add that if you want. And by these operations, you transform in, after stabilizing it, you transform into the identity. And the proof is simply, well, what I know, the statement that M is 0 in the Whitehead group the statement that M is 0 in the Whitehead group means that if you take the image of M in GL infinity of Z of G, it's in the group generated by elementary matrices and the 1-by-1 matrix plus minus G, where an elementary matrix has ones down the diagonal and exactly one non-off diagonal entry that's not 0. Alpha, an arbitrary element in the integral group ring, times the matrix with a 1 in the ijth place and 0 everywhere else. Your I is not equal to J. Okay. Well, if that's true so there's a finite sequence, so M in this infinite matrix group can be written as a product of these matrices, this 1-by-1 matrix and these elementary matrices. Well, if that's true in the, that's a finite product, of course. If that's true in the infinite matrix group, these are 1-by-1 matrices. These matrices are all in finite GLNs. There are only finitely many of them. So all these are in some GLN ZG, where of course the size will depend on the original matrix M. So not only in the infinite matrix group, but in some finite matrix group, I can write M as a product of these matrices. And these matrices exactly do the column operations. The first one multiplies the first column, in fact, by plus or minus G. And the second does the elementary operation left multiplication by this matrix. Oh, I guess I need to say, if M is a product of these matrices A1 to AK, these are elementary matrices or 1-by-1 matrices, then M times AK inverse A1 inverse is the identity. And the inverse of any elementary matrix, or plus minus G, is another matrix of the same form. So you can act on M from the left by these elementary matrices and multiplying by and the 1-by-1 matrix plus minus G and get it down to the identity. But these elementary matrices just do column operations. The AI inverse do column operations on M. Okay. So that's the proof. And this brings up a mistake I made last time. Last time I defined K1 as, I mean, it's not a mistake, but it's misrepresenting things. I said K1 was the quotient of GL, the infinite matrix group, by the normal subgroup generated by the elementary matrices. In fact, that's true, but it's the group generated by the elementary matrices. They form a normal subgroup. So, and I'm using that here. I need to multiply by elementary matrices, not conjugates of elementary matrices. Okay. So that errata from last time. So where we got to at the end of last class, we defined, of course, the Whitehead torsion of an isomorphism, L to L prime. Everything here are free modules over Z pi 1. So I'm now working over Z of G. So these are finally generated free modules over Z of G, and they have given bases. Okay, so we defined the Whitehead torsion of an isomorphism alpha. Then we defined the Whitehead torsion of a chain complex C star, again, chain groups free with bases, if the homology of C star is 0. And then I defined the Whitehead torsion of a chain map between chain complexes, inducing an isomorphism on homology. Remember, the construction there was to take the mapping cylinder of this chain map. It inherits bases. It's free over the integral group ring. It inherits bases, and its homology is trivial. And the homology, the Whitehead torsion of this map is the Whitehead torsion of the mapping cylinder chain complex using the previous definition. And then I passed from algebra to geometry by saying if we have finite CW complexes, X and Y, and a continuous map from, well, a cell map a cellular map that's a homotopy equivalence, then F star maps the CW chains of X with coefficients in the fundamental group to the cellular chains of Y with coefficients in the integral group ring of the fundamental group. The fundamental groups are the same, so let me just call it X. And the fact that F is a homotopy equivalence, these chain groups are also the chain groups of the universal covers. And this is the map induced by the universal cover, some universal cover of F. Okay. So if F is a homotopy equivalence, this map induces an isomorphism on homology. Because to be a homotopy equivalence, weak homotopy equivalence, is the same thing as inducing an isomorphism on the fundamental group and a homotopy equivalence on the universal covers. And a homotopy equivalence on the universal covers is just isomorphism and homology, since these are simply connected. Okay, so if you have a cellular map, the cell complexes have bases, which you get by attaching the cells to the base point by paths. And so those give you bases for these complexes, and you have the white-edge torsion of F star, which is the white-edge torsion of this map. You change bases by connecting the cells using different paths. You simply do elementary operations on these bases, and so you get the same white-edge torsion. So that's the white-edge torsion of a cellular map. But now if we just have a continuous map from X to Y, where X and Y are finite CW complexes, it's a homotopy equivalence. Then we can define its white-edge torsion. It's the white-edge torsion of any cellular approximation. And I argued that that's a well-defined definition. If you have two cellular maps, which are homotopy equivalences and homotopic, their white-edge torsions are the same because you can make the homotopy between them a cellular map from X cross I into Y. And you have the inclusion of X cross 0 and the inclusion of X cross 1. Those are simple homotopy equivalences. So the white-edge torsion of this cellular homotopy is the same as the white-edge torsion at either end. And so you get a well-defined notion of the white-edge torsion of any continuous map between finite CW complexes. And I want to use that for smooth manifolds. So now let M be a C infinity manifold. Well, smooth manifolds have smooth triangulation. So M has a smooth triangulation. That is to say, there's a simplicial complex K and a homeomorphism from K to M such that the image of each simplex is a smooth embedding. Okay. It has lots of smooth triangulations. There are many ways to get them. One is embed M in Euclidean space, take a fine triangulation of Euclidean space, shift M slightly so that it's in general position with respect to that triangulation, look at the way M intersects the various cells. That will give you a piecewise cell structure on M, and then you just triangulate that. But there are many other ways to do it. But the point is that any two of these smooth triangulations are combinatorially equivalent. So if K and K1, K naught and K1 are smooth triangulations, there exists a common subdivision as simplicial complexes. So there's a subdivision of K naught prime, a subdivision of K1, K1 prime, and a simplicial isomorphism between them, so that compatible with the map to M, so that the simplicial isomorphism is homotopic to the identity by, in fact, a small homotopy. So you can associate to any smooth manifold a triangulated manifold. Thus, if you have a homotopy equivalence between smooth manifolds, these are now triangulated, and with respect to the triangulations, F has triangulations are in particular CW complexes. So these are finite CW complexes. These are compact manifolds. So M1, M0, M1, compact. These are finite simplicial complexes, and therefore this homotopy equivalence has a white-head torsion given by these triangulations. If you take different smooth triangulations, because of this common subdivision, you'll get the same white-head torsion. And we're, of course, most interested in the case of an s-cobordism. So suppose this is the inclusion of the negative boundary in an s-cobordism. Well, these are smooth manifolds, so you have the white-head torsion of the inclusion. Just called the white-head torsion of the s-cobordism. Okay. All right, so that's the general theory of geometric structures and white-head torsions, but I need to connect it up to Morse theory. So there's another way to associate a white-head torsion to an s-cobordism, and that's to use the Morse complex. So let me start by defining that. So remember, the Morse complex, we have a self-indexing Morse function. So it has critical points. PI are the critical points. Normally, to define the Morse complex, well, to define the ordinary Morse complex, I have to choose, well, I take a gradient-like vector field. I need that. Then I orient the descending manifolds from the critical points, and I order the critical points of each index, I guess. That's all I have to do. With these choices, we took CK of F and chi to be the free abelian group generated by the critical points of index K. And the boundary map from CK to CK minus 1 was given by, well, you can give it in purely homological terms, but it's also nice to think about it assuming that you perturbed chi so that the descending and ascending manifolds are transverse is given by intersection numbers of the descending manifolds of critical points of index K at some intermediate level with the ascending manifolds, critical points of index K minus 1. So S, P, K minus 1 intersect S, Q, N minus K in these intermediate levels. And the orientations allow you to associate signs to these intersections. Well, that's the Morse chain complex, and we showed that the homology of this complex is the homology of W, comma, boundary minus W. All right. Well, now I need to work over the fundamental group, and I'm going to make choices and constructions very similar to what we did in the case of a CW complex, but it's in the context of Morse theory. So now I want to define a chain complex over the integral group ring. So I fix a base point, say in the boundary minus, doesn't really matter. Okay, I want to define a chain complex, not of free abelian groups, but rather of free Z pi 1 modules. So to do this, in addition to the above choices of orienting the descending manifolds and ordering the critical points, I also choose for each P, critical point P, choose a path, I'll call it omega of P, from the base point to P. Well, yeah, to P. So here's P, here's the base point out here. I have to have an omega of P. One for each critical point. Okay. Then the chain group with coefficients in the integral group ring of the fundamental group is simply the free Z pi 1 of W module generated by the critical points of index K. So instead of taking the free abelian group generated by these points, I take the free Z pi 1 module generated by these points. Now, what about the boundary map from CK with these coefficients to CK minus 1? Well, again, what I want to do is take a point P of the critical point P of index K and a critical point Q of index K minus 1, and I want to compute the coefficient of the generator Q in the expression in boundary of the generator P. So P brackets represents the element in the generator in the kth chain group, going with the critical point P. Brackets Q is the element in the K minus first chain group that goes with the critical point Q. And to know the boundary of the generator associated with P, I just have to tell you what all its coefficients are with respect to the basis given by the critical points of index k minus 1. And if I know the boundary for the generators of the chain group in degree P, K, I'll know the boundary in general. Well, this coefficient is computed in terms of the intersection of the descending manifold from P and the ascending manifold from Q in an intermediate level in F inverse, what is it, K minus a half. So I might have a picture like that. This is the descending manifold for P. Here's the ascending manifold for Q. They're complementary dimensions in this n-1 manifold, this level set. And so we have points of intersection. I'm assuming that I've chosen chi, so they're transverse. I need to associate a sign. I need a sign plus minus 1 and a group element in the fundamental group associated to this point of intersection, to each y in this intersection. Okay. Well, the sign is just the sign as before. It calculates the intersection number from all the orientations. So the sign is as before. No mystery there. What about the group element? Well, we have the base point over here. We have P, Q, and here's a point of intersection. We have paths, omega P and omega Q, from the base point to P and to Q. Now the descending manifold is a disk, so I'm free to choose any path. We could do the sort of straight line path in the disk structure from P to Y, alpha, call it. And then I could do straight line path from Q to Y, call it beta, and I can make a loop, omega P, alpha, beta inverse, omega Q inverse. And that's a loop based at omega naught, and so that's an element in the fundamental group of W based at W naught. It, of course, depends on my original choice, which is fixed for this discussion, of these paths, omega P and omega Q, and it's independent of the choice of alpha and beta, since alpha and beta are in simply connected manifolds, disks. Okay. So this gives me a well-defined element, which I'll call G of Y. So I have epsilon of Y, which is a sign, and G of Y for each Y in this intersection. And the coefficient of Q in boundary P is the sum over the points of intersection of epsilon Y, GY in the integral group ring of the fundamental group. Okay? So I do exactly what I did before, except now I have these paths connecting things to the base point, and that allows me to associate group elements So I sum up over the intersection points, not just of the signs, but of the signs with these group elements. And I get an element in the integral group ring of the fundamental group, and that defines a boundary map. Now you have to prove that boundary square is 0. And I'll do that the same way I did it in the CW case. Let's consider the universal covers. And F tilde lifts to map on the universal cover, and chi lifts to a gradient-like vector field for this map. We're not in the finite, not in the compact case anymore, but nevertheless, this is a Morse function. This is a gradient-like vector field. The choice of paths omega p gives a lift p tilde for each critical point p. Namely, downstairs in the manifold, you have this path omega p. You simply fix a base point upstairs above omega naught tilde, fix that once and for all, and then you lift the path, and it's starting at omega naught tilde. Its other end will be a critical point above p, which is the one that's determined by that choice of path. Okay. So the fundamental group acts by covering transformations on the universal cover, and it acts freely on critical points of index k. And the cross section, the p tilde give a cross section. That is to say, these choices for each p downstairs, the choice of p tilde produces an element in each of the free orbits of this action. So now we can form the Morse chain complex for this map on the universal cover and the gradient-like vector field with ordinary integer coefficients. And this is in fact identified with the chain complex downstairs with z pi 1 of w coefficients. And the boundary maps agree. So boundary squared here is 0 because this is an ordinary Morse chain complex. So that implies boundary squared, as I defined it downstairs, is also 0. It also shows you that if W is an s-cobordism, then this Morse complex that I've defined with the z pi 1 coefficients computes the homology of W tilde modulo boundary minus W tilde, because that's what this Morse complex computes. But that's 0 if we have an s-cobordism. So the homology, if you have an s-cobordism, the homology of the chain complex that I've defined is 0. Okay. Well, now we're in position to define the Whitehead torsion. The Whitehead torsion of this chain complex is the Whitehead torsion of the Morse function, or of its chain, the Morse function or its chain complex, whichever you prefer. Okay. So that's another way to get at Whitehead torsion, using the critical points and the descending manifolds downstairs with paths, or upstairs having chosen lists of the critical points, whichever you prefer. And now there's an easy exercise, a proposition, that the two definitions I have of Whitehead torsion, so that boundary minus W, W, B, and H s-cobordism, let F be a self-indexing Morse function, chi a gradient-like vector field for F, then the Whitehead torsion of this Morse complex, as defined above, is the Whitehead torsion of the inclusion of boundary minus W into boundary W, as defined by, because these are smooth manifolds. Smooth manifold definition and Morse definition. So the two ways that we have of defining the Whitehead torsion of an s-cobordism, either by realizing these are smooth manifolds, triangulating and using the cell structures to define Whitehead torsion, or by using the Morse complex, give the same answer. I'm not going to prove this, but I'll sketch it briefly. Remember, if W is you have a Morse function on W with exactly one critical point. We defined a retraction from W onto boundary minus W, F inverse A, union a disk of dimension equal to the index. Okay. This was a deformation retraction. That turns out to be a simple homotopy equivalence. It's not a hard argument. It's Whitehead. A simple homotopy equivalence. I'm not sure I defined this last time. If I didn't, I'll say what it is now. Even if I did, I'll say what it is now. You have a homotopy equivalence of manifolds that have geometric structure, so that you can define the Whitehead torsion of that homotopy equivalence. The homotopy equivalence is said to be a simple homotopy equivalence if the Whitehead torsion is trivial. So this contracting map is a simple homotopy equivalence. And then you go by induction. W to the cell complex made by attaching cells for the attaching cells to boundary minus W, one cell for each critical point. This is a simple homotopy equivalence. And this gets you from the cell complex the Morse complex to the CW homology, because here you're calculating using the CW homology. Here you're calculating using, say, the triangulation, but the CW homology is exactly the Morse homology. So the CW homology becomes the Morse homology, and this equivalence tells you you have a simple homotopy equivalence. I'm not going to say anything more about that. It's a nice exercise if you'd like to do it for yourself. All right. Now, I think I'm ready for the s-cobordism theorem. Let me just see here if I'm missing anything else. I'm sorry, the s-cobordism theorem. Yeah, okay, now I'm ready for the s-cobordism theorem. So here's the statement. Let let's say it this way, let W boundary minus W boundary plus W be an h-cobordism. So W is a compact manifold with boundary, and the inclusion of either boundary minus or its complement boundary plus into W is a homotopy equivalence. Suppose dimension of W is at least 6. Then W boundary minus W boundary plus W is diffeomorphic to boundary minus W cross I, boundary minus W crosses 0, boundary minus W cross 1. So you have a product cobordism if and only if the Whitehead torsion of the inclusion of boundary minus W into W is trivial, if and only if the Whitehead torsion of any self-indexing Whitehead torsion of the Morse complex C star F chi fundamental group is trivial. Okay. So in the case of the s-cobordism, we were working in the simply connected world, and the Whitehead group of the integral group ring of the trivial group, well, it's just a Whitehead group of Z. K1 of Z is, so on the side here, K1 of Z is plus minus 1 given by the determinant. So the Whitehead group of Z, so the Whitehead group of the trivial group is K1 of the integral group ring of the trivial group, which is K1 of Z modulo plus or minus 1, K1 of Z modulo plus minus 1, which is trivial. So in the special case, when the fundamental group is trivial, the Whitehead torsions, there are no Whitehead torsions. The groups are 0, so these two conditions hold, and therefore the s-cobordism is a product by this theorem. In the non-simply connected case, there are lots of interesting s-cobordisms. I won't prove it, but it's not very hard to show that given any element in the Whitehead group and given a fundamental group G and given a manifold W with that fundamental group of any dimension actually, and any element in the Whitehead group of G, you can construct an s-cobordism whose Whitehead torsion is that element, starting with boundary minus W. So that's another aside. Given boundary minus W, pi 1 boundary minus W equals G. Maybe I need dimension of W to be, well, 2, I guess. Boundary minus W to be 2. And any element in the Whitehead group of G, there exists an s-cobordism W, boundary minus W, with Whitehead torsion G, alpha. So there are lots of non-trivial s-cobordisms. There's in fact a bijection, in fact a group isomorphism, between the s-cobordisms off of a manifold W and the Whitehead group. You can concatenate s-cobordisms, and that simply put one on top of the other. That simply adds Whitehead torsions. So there's a way to turn this into a group isomorphism. Anyway, there are lots of non-trivial s-cobordisms. Another aside, you might ask, what happens if I turn an s-cobordism over? Clearly, it's a product one way, if and only if it's a product the other way. So that says if the inclusion of boundary minus into W has 0 Whitehead torsion, by flipping it over, we see that implies that boundary plus into W has 0 Whitehead torsion. So that suggests that the Whitehead torsions ought to be related, and indeed the Whitehead torsion of the inclusion of boundary minus W into W is the opposite of the Whitehead torsion of the inclusion of boundary plus W into W. So you flip an s-cobordism over, you change its Whitehead torsion to its negative. So that's an interesting thing. You take any s-cobordism from W to W prime, boundary minus W to boundary plus W, W, you flip it over. So minus W, flip it over and stick it onto itself. This is a product in high dimensions, because the Whitehead torsion of this one is the opposite of the Whitehead torsion of that one. So the Whitehead torsion of this whole thing is trivial, and therefore it's a product. So you have these interesting s-cobordisms that lie inside products. The way you've sliced is somehow non-trivial. All right, so much for the asides. Let me turn to the proof. Well, one direction is fairly easy, and in fact holds in all dimensions. If boundary minus W, if W boundary minus W is isomorphic to boundary minus W cross I, comma boundary minus W cross 0, then the inclusion of boundary minus W into W has trivial Whitehead torsion. Anytime you include a cell complex into its self-product interval, that inclusion has trivial Whitehead torsion. We've already seen the Whitehead torsion of the map of smooth manifolds and the white-edge torsion of the Morse complex are the same. So these two are both 0. So that proves one direction, the non-interesting direction. If the manifold is trivial, then the white-edge torsions vanish. And that's true in all dimensions. The more interesting direction, which is this algebraic invariant that describes the topology or geometry, requires the dimension restrictions. So now I'm going to assume n is at least 6, as I had to for the s-cobordism. Okay. F is a Morse function. Self-indexing. And chi is a gradient-like vector field. And I'm going to follow the proof of the s-cobordism theorem as far as I can. So the first step in the s-cobordism theorem was to remove critical points of index 0, 1, and then flip it over n minus 1 and n. These arguments work exactly as before. Okay, so maybe I'll say one thing. There's one point where they're slightly different. Remember when I canceled the critical point of index 1? So if I had a critical, so here's boundary minus W. I have a critical point of index 1. Let me draw the one handle. What I did was I said, all right, draw this arc across the one handle that meets the ascending manifold out of the critical point in a single point, transversely in a single point. And then I said, well, since boundary minus W is connected, I can close this up to a loop by adding an arc in boundary minus W. And then over somewhere else, at a higher level, I created a birth death. I had the descending manifold for the birth, and I pushed this up to the same level. And I said, okay, here's a circle, here's a circle. Those are two circles in a 5 manifold. Since the 5 manifold is simply connected, they're homotopic, and by general position, they're isotopic. Well, that argument can't quite be right here because this level is not simply connected. So the fundamental group here is pi 1 of W, well, boundary minus W, pi 1 of W. So the same argument as before, with the dimensions of the handles you add to get from here to W, shows you that that argument works to show the fundamental group of this is identified with the fundamental group of W. So here I have a trivial element in the fundamental group of W, bounds a disk clearly. I need to make this guy trivial. Well, okay, I connected the two ends here by a path, and then I push it up, I get an element in the fundamental group of W, which is the same as the fundamental group of boundary minus W. I want that element to be trivial. Well, no reason that it is trivial, but I'm free to vary it by any loop in boundary minus W. Well, since I can vary it by any loop in boundary minus W, I can change the homotopy class of this loop up at the higher level by an arbitrary element in pi1 of boundary minus w, which is pi1 of w. So by making an appropriate choice of this arc connecting the feet of my arc that cross the one handle, I can arrange that this is homotopically trivial. These are then homotopic circles in this 5 manifold. You connect them by an annulus. So that's the only place in the arguments for 0 handles and 1 handles that the fundamental group comes in at all. Okay. So I now assume that F has critical points of index only from 2 to n minus 2. And I have this chain complex free over the integral group ring. Well, I had this lemma about these chain complexes that says if you have a chain complex, like this one, finitely generated, free and finitely generated, that you can, by adding trivial complexes of the form boundary mapping di plus 1 onto di identity matrix, so by adding a finite number of trivial complexes with trivial homology and trivial torsion, because the boundary map is just the identity between 2 free modules, you arrive at in my case here, I'm going to arrive at a situation like this. I have C n minus 2 to A n minus 2 plus B n minus 2. So I'm drawing the boundary map, A n minus 3 plus B n minus 3, and so on, down to A2 plus, A3 plus B3, down to A2. And there is no B2. So the chain complex looks like this. The basis, the A's and B's are free. AI and BI free. The bases, so this is, sorry, this should be n minus, got my numbering screwed up here. This is n minus 3, n minus 4. So you have the bases for the, after making elementary transformations, you have the bases for the CI, which split as part of the basis makes A, the basis for A's, and the other part makes the basis for B's. The boundary map is an isomorphism from the B's to the next lower A's. And the matrices here are the identity. And here you get alpha, where the Whitehead torsion of alpha is the Whitehead torsion of the chain complex. Okay. So that's a little algebraic lemma using the algebraic fact that I stated at the beginning about stably a matrix has trivial Whitehead torsion if and only if you can do elementary transformations on a larger version of it to turn it into the identity. Use that and the fact that you also have to know that these modules are stably free, and thus by adding more free modules, you can make them free. Anyway, it's an easy exercise in chain complex theory or linear algebra if you want. to produce this setup. Okay. Now, so that's just a linear algebra fact over the integral group ring. I need to replicate, so what I used in producing this new picture of a chain complex, so I started with my Morse chain complex. I'm going to do things to it, and the things I do to it are of two forms. I stabilize by adding trivial chain complexes like this one. And then I change basis by elementary transformations here to get this. Okay. I have to mimic those operations geometrically by adding critical points and doing handle slide. So first of all, how do we, to add a complex of the form di plus 1 di with the identity matrix for the boundary map, what do you do? Well, let's just add, do the case of rank 1. So rank 1, I need to add 2 critical points, one of index I, and I plus 1 with the boundary map being the identity, matching them, shall we say. So I would need 2 critical points, one of index I, one of index I plus 1, with a single flow line, transverse flow line between them. And I would want the group element, I would want PAS here, so that the group element formed by that was trivial. That's what this says. Well, this is exactly what a birth does. You go out into, at some level, into the s-cobordism, you find a little ball where the function is non-zero and the vector field is in the xn direction, and you replace that by a birth with 2 critical points connected by index I and I plus 1, connected by a single flow line, transverse flow line. And now you want to connect things over to the base point. Well, you just use the same loops here and here, and then you'll get a trivial, the boundary map will be plus 1 times the identity if you do that, which is exactly the boundary map you wanted to achieve. So stabilizing is just achieved by births. It's exactly what births give you. And you do births at different levels to get these complexes set in at different levels. Now you need to do elementary transformations. Let's talk about those. So changing the sign is just changing the sign of the descending manifold. Permuting the columns is just reordering the critical points. But the last thing I have to do is I have to add to a basis element E1. So if I have a basis E1 up to ER, I need to replace it by, let's say, E1 plus alpha E2, E2 up to ER. Or, I mean, 1 and 2 could be anything, but let me just take those. Where alpha is an arbitrary element in the integral group ring. So I need to do a handle slide. So E1 is the basis element going with critical point P1, which is somehow connected to the base point. And E2 is related to a critical point P2, which is somehow connected to the base point. Okay, and at this intermediate level, P1 and P2 have the same index, K, let's say. So we have an SK minus 1, the descending manifold for P1, and we have an SN minus K minus 1, K, right, plus for P2. So remember, the way we do the handle slide is we have to move the first one up slightly above the other critical points of index K. And then in order to do the handle slide, we need to choose a path, an arc, gamma, from the descending in this level, from the descending manifold of P1 to the ascending manifold of P2. And then we just do a tab move. If we have the descending manifold of P1 here and an arc connecting it to the ascending manifold for P2, we simply do this sort of move, producing a point of intersection, which, depending on how you arrange the signs, can be a plus or minus. But now I have to record not only the sign, I have to record a group element. So I have my path omega P1 and omega P2. And then I connect from P1 to this point, go across this arc, go back up to P2 and come back down. So I get a loop. If this arc is gamma, I get a group element, G gamma, in the fundamental group based at W naught, which is just the path up to P1, a path in the descending disk from P1 down to the start of gamma, in gamma, then a path from the end of gamma up to down to P2, and then omega P2 inverse. Okay. And that's an element in the fundamental group. Let me draw a better picture here. So here's my critical point P1. Here's my critical point P2. I have a path to P1. I have the descending manifold from P1. I have the ascending manifold from P2. There are one complementary dimension minus one. The sum of these two dimensions is one less than the dimension of the slice. I choose an arc gamma like this. I have my paths omega P1 and omega P2 from the base point to P1 and P2. I form a loop. I go up to P1. I come down the descending manifold to the initial point of gamma. Then I use gamma. Then I come back up to P2 in its ascending manifold, and then I close using gamma P2. So this is alpha, and this is beta, and this is gamma. Alpha and beta are irrelevant because they lie in disks. Okay. So if I do the handle slide that I'm talking about using gamma, so using gamma changes E1, which is the basis element going with P1, to E1 plus or minus, depending on the choice of orientation, G of gamma, E2, and then E2 and so on are unchanged. Okay. Well, I want to be able to do an arbitrary sign times an arbitrary group element. Well, to do that, I use the freedom I have in gamma. gamma is any arc connecting these 2 points in this level. The fundamental group of this level is the same as the fundamental group of the manifold. Therefore, I can vary gamma in this level by any loop, and therefore change this, the homotopy class of this loop by an arbitrary element in pi1. So as gamma varies, G of gamma is an arbitrary element of pi1 as gamma varies. If you choose different homotopy classes of gamma, you'll get arbitrary group elements here. So I can change E1 to E1 plus or minus GE2 for any G in pi1. Well, do that operation over and over again. So repeat using different signs and different group elements. You can change E1 to E1 plus alpha E2 for any alpha in Z pi1. So you have to do many slides in order to get an arbitrary group element. Okay. So handle slides allow us to do an arbitrary change of basis over the fundamental group. And therefore, again, using this stability result, maybe I'll have to stabilize even more. I can do these handle slides and produce the chain complex, this algebraic chain complex. Okay, so that's in general. But now let's invoke the hypothesis that we have a simple, an s-cobordism, that is an h-cobordism with trivial Whitehead torsion. Well, the Whitehead torsion of the h-cobordism is also the Whitehead torsion of this one remaining element that wasn't pinned down. But if it's trivial, again, by stabilizing, I can make alpha also the identity. So so using the hypothesis that the Whitehead torsion of the inclusion of, that we have an s-cobordism theorem, that we have an s-cobordism, using that hypothesis, we also make alpha equal the identity. So the bases here and here, so that alpha is the identity. So I get this picture from top to bottom. Now it's time to cancel the handles. Oh my goodness, I only have 2 minutes to cancel the handles. All right, well, I'm gonna have to finish that next time. To cancel the handles, I'm gonna use the non-simply connected version of the Whitney trick. So I'll just tell you what we're going to do, and then I'll do it next time. If we have a pair of a pair of intersection points between an ascending and descending manifold that we want to cancel, well, again, we need to put in a disk across here. Well, now we're in a non-simply connected manifold. There's no reason to think this loop bounds the disk, but the homotopy class of the loop is, sorry, wrong picture. The homotopy class of the loop is determined by the intersection, group element intersection at y0 and the group element intersection at y1. So if epsilon y0 g y0, so this is the sign of intersection at y0, this is the group element of intersection at y0, plus epsilon y1 g y1 equals 0, then we can apply the Whitney trick. So we can only cancel when the signs cancel and the group elements are the same. This equation means the signs are opposite and the group elements are the same. So I'll show you why that's true next time. It's just, you look at the Whitney argument, this is exactly what the Whitney trick, this is exactly what you need. And then from here, it's easy to see the non-simply connected version of the Whitney trick, what the statement is. But I've run out of time for today, so I'll have to do that next time. Any questions? I have posted a version of this material online, but as I was preparing today, I decided to make a few changes and add a little bit of material. So I'll read over what I was doing right before this lecture and post it later on this afternoon. Somebody asked me about the finding the lectures. How do you find my lectures online? What do you go to? They're on YouTube. What YouTube channel do you go to? Anybody know?
Yes, I'll post a link in chat.
Okay, great. I think it was Alex. You were the one who asked, right?
Yeah, that's right.
Okay. All right, well, I'm sorry I didn't finish today. I was certainly expecting to, but I will briefly wrap up. It won't take much longer. The Whitney trick and how you apply it. And then I'll start on Bott periodicity, which is great theorem number 2 out of the 20th century, as far as I'm concerned. So did you post it, Jesse?
No, I had to find it. Here it is.
Okay. I mean, I think it's called Morse Theory Lectures, capitalized with spaces, but maybe that doesn't identify it.
It is. The link is now in the chat. So for anyone who doesn't have it.
I see. Great.
Thank you. Yeah, it works.
Yeah, thanks. Okay. See you. Thanks a lot, Jesse. Thank you. See you next week.